inverse of quadratic. But yeah, let's just see how our time goes this evening. Anyway, if there's anything that I do or say, then please, that's wrong, please do stop me and let me know. Nicole, I hope you also keep an eye on my adding and subtracting, because we all know it can be a little bit iffy at 5 o'clock in the evening. I'll try not to make any mistakes. Okay, so let's first consider the function f of x equals 2x minus 4. Now we recognize that that is a linear function because it's in the form y equals mx plus c, right? So we are saying when we write f of x equals 2x minus 4, we are saying that there is a rule that transforms the given values or domain values, x values, into values in the range, y values, outputs, using the rule 2x minus 4. So for example, if we want to calculate the value of y when x is 3, we would sub 3 in, wouldn't we? So we would calculate f of 3, and we would do that by subbing 3 in here, and we would work out that our answer in this case would be 2. All right, so that is us using our rule and working forward, so from input to output, right? The rule that reverses this process and transforms 2 back into 3 is called the inverse of the original function. And we would obtain that by interchanging x and y in our original function and then making y the subject of the formula. So this new function that we are obtaining has different notation. So when we are talking about functional notation or the inverse function, our functional notation looks like this. So if we were talking about f of x equals 2x minus 4, we would write the inverse of this as f minus 1x. Okay, and this notation over here, f to the power of minus 1x, is our inverse notation. All right, so it doesn't have anything to do with exponents. It isn't a reciprocal. It's the way in which we write an inverse. Okay, so the inverse of f of x, we would write it as f minus 1x. Okay, so what we are doing here, if we want to reverse this process and transform 2 back into 3, all right, what we have to do is we have to interchange x and y. So if y is equal to 2x minus 4, then we would say that, sorry, it would be 2x, I left that off. 2x, sorry, I beg your pardon, sorry, no, beg your pardon. Then x would be equal to 2y minus 4. So what I've done here is I have interchanged x and y. Does that make sense to everybody? So where y was, there's now an x, and where x was, there's now a y. This interchanging of x and y is exactly the same as reflecting the function over the line y equals x. Okay, so when we are working out, or when we're working with inverse functions, what we are doing is we're actually reflecting our function over the line y equals x. Now, our line y equals x, just very quickly, just remind you what that looks like. If this is a normal Cartesian plane, there's my y-axis, there's my x-axis. The line y equals x has a positive gradient, okay, and it goes through the origin. All right, and the reason why we call this line y equals x, it's actually in the form y equals mx plus c. So c is 0 because it goes through the origin, and the gradient of this line is 1. Okay, so what we find is that if we've got an input of 1, we've got an output of 1. That's why y equals x. Or if we've got an input of 2, we've got an output of 2. And similarly, if I had an input of -3, I would have an output of -3. That's why it's called the line y equals x. It is also one of the axes of symmetry of your hyperbola if it hasn't been reflected. Okay, so you should recognize it from there as well. Now what we need to do, that we have interchanged x and y, is we need to make y the subject of the formula. Okay, so what I'm going to do is I'm going to rewrite this as 2y minus 4 equals x. And then I'm going to take the 4 over to the other side, the negative 4 term. Okay, so this is now going to be x plus 4. And in order to make y the subject of the formula, I now need to divide through by 2. So I'm going to divide every single term in the equation by 2. And that now leaves me with 1y. That's what I want. Plus 1 in front of the y is equal to 1/2 x, or you could write x over 2 if you wanted, plus 2. Okay, so we would say that the inverse of y equals 2x minus 4 is the line y equals 1/2 x plus 2. So what this rule would do is that it would transform 2 back into 3 again. All right, so and again, what they've done there is they've written it using the inverse notation. They've said, or we can write it as f to the power of minus 1, x equals 1 over 2x plus 2. All right, now what they've written here in the notes and what I've written is exactly the same thing, right? What they've done is they've just put x plus 4 over 2, whereas I've just split it apart. So whether you keep it together or split it apart, it really doesn't matter. What I wanted to bring your attention to is this. Remember up in the beginning, right, I subbed 3 into this rule and I ended up with 2. So now if I sub 2 into the inverse, I end up with 3. So that's what we should see over here as well. Okay, so if I sub in 2, I should end up back at 3. Okay, so 1/2 times 2 would be 1, and 1 plus 2 equals 3. Okay, does that make sense to everybody? Everybody good at this point? Okay, so I've left the explanations there for you so that if you did want to come back and watch these lessons at a later stage, there are notes there for you that you could copy down or refer back to, or whatever the case is. All right. Now, one of the things that we would get you to do is we would get you to sketch these graphs. All right. So I'm going to show you how we would do that. And it's really very easy when it comes to sketching linear functions, because all you need are 2 points. And the 2 points that we would need would be the x-intercept and the y-intercept. All right, so super easy. Okay, so let's do the graph of the original function first. Right, so if we wanted to now sketch this graph, we want to work out what its y-intercept is. Okay, so remember, for the y-intercept, you don't have to write this. I'm just writing this to be thorough for you. We're going to let x be equal to 0. So we would say y equals 2 times 0 minus 4, and that would be equal to negative 4. All right, so our y-intercept is 0 and negative 4. Our x-intercept, where we would let y be equal to 0, we would say 0 equals 2x minus 4. I can take my 2x over to the other side. Does it make sense that I've got that? Again, if I took the 4 over, both of them would be positive on opposite sides of the equal sign. Divide both sides by 2, and x would be equal to 2. So the coordinates at the x-intercept would be 2 and 0. So now when I go ahead and I go and sketch this line, let me just highlight it in purple. Ooh, do I have purple? Okay, let's go with that. Okay, it's going to be this line over here. Okay, so there's its, it's not a very nice purple, is it, guys? Okay, so there's its x-intercept and its y-intercept. You would just plot those 2 points, grab a ruler, and draw the line. Super easy. If they now wanted us to draw the graph of the reflection of this over the line y equals x, or if they want us to draw, let's choose a different color. Let's go with pink. So now we're going to do this. We are sketching the graph of y equals 1/2 x. I think it was plus 2, wasn't it? Yes. And what you would discover when you work out the x and y intercepts is that they've actually switched sign, and that makes sense because we've reflected it over the line y equals x. But I'm going to point that out to you a little bit more now once we've just calculated these points. All right, so again, for our y-intercept, we're going to let x be equal to 0. So we would have y equals, so that would give us 2. See there, the coordinates are 0 and 2. For our x-intercept, we're going to let y be equal to 0. So that's half x plus 2. So now we would end up with negative 1 over 2x equals 2. Sorry, I'm writing on the side here. Which means that x would be equal to, so in other words, what I must do is multiply both sides by negative 2. Maybe I should write that for you guys, although I'm sure you know this. And that's why x would end up being negative 4. Okay, so what's super important here to realize, if we compare the purple with the pink, right? With the purple, let's get a better color. All right, our y-intercept was 0 and negative 4. With our pink graph, our y-intercept is 0 and 2. Can you see how it's switched around? Same story over here. Let's highlight this one in a different color. Okay, there was our x-intercept at 2 and 0. And now here's our x-intercept at minus 4 and 0. Okay, so this line, pink, purple, what color are we going with? Pink. This line over here, okay, that is the line y equals half x plus 2, has been reflected over the line y equals x. Can you see what was your y-intercept is now your x-intercept, and what was your x-intercept is now your y-intercept. Okay, that's what happens when we reflect over the line x equals y. Y becomes x and x becomes y. Everybody happy with that? Does that make sense? Any questions? Yes. Okay, yeah, this beginning bit is generally the easier part. Okay, and then if they asked you to determine the coordinates at the point of intersection, all right, that's the only other thing that I was just going to run through quickly here, is you would just equate those two to one another. Okay, so determining the coordinates at the point of intersection, there's a space over here for us to do it. We would let f of x, and you don't have to write this, I'm just writing it for you. We would let those two be equal. Okay, so in other words, 2x minus 4 would have to be equal to half x plus 2. I'm of the opinion that if I'm trying to solve a linear equation and I've got a fraction in it, I always just get rid of the fraction first. If you wanted to take the half x over to the other side and then work with a coefficient that was a fraction, you're very welcome to do that. I like to get rid of the fraction straight away. So I'm going to multiply every term by 2, and that's going to give me 4x minus 8 equals x plus 4. And then on this side, I'm going to end up with 3x, and on this side, I'm going to end up with 12, and x would be equal to 4. And of course, because I'm reflecting over the line y equals x, it means that y would be equal to 4 as well. Okay, so there we go. All right, so that's how we arrived at this pair of coordinates over here. Okay, so please also note that they intersect one another on that line, on the line y equals x. Okay, and they would do so every single time. All right. Is everybody happy with that? That's fine, Boyshep. I'm glad you joined us. No problem. Okay, just a couple of things to also note taking forward, all right, is that the function f of x equals 2x minus 4 is a one-to-one linear function. Its inverse is also a one-to-one function, and the two graphs are symmetrical to each other about the line y equals x. Okay, All right, now, what I wanted to offer you was an opportunity to just do what I've done over here. I think it's nice that we should have an opportunity to do that. All right, just one, and then we can certainly move on. So what I'm going to give you is 2 graphs. You don't have to do both. All right. The easier one is B, and if you were looking for a little bit more of a challenge, then I would rather do E. Okay, so what you would do is you'd write down, so it gives us a list of instructions here. So for each function, determine the inverse. So that would be the first thing that you were going to do in the form f to the minus 1 equals x. Second thing, draw an edge sketch of both functions on the same set of axes. Draw in your line of symmetry, and then determine the coordinates at the point of intersection on both graphs, and then indicate that in the diagram. So I just want you to do one. I don't want you to do both, and then we can move on to the quadratics. Is that okay? All right, so I'm going to give you guys, you probably shouldn't need more than about 5 or 6 minutes. And Nicole and I are here if you need us to ask any questions. Okay, we're just going to be quiet for a little bit and let you do that. Okay. Cool beans. Yes, Kumo it is. It is. So it's in the form y equals mx plus c. So f of x equals minus 2x plus 0, essentially. So yeah, that's why I put it in there, Kumo, because it doesn't have a positive gradient, it's got a negative gradient. That's why it's a little bit more challenging. Yeah. So yeah, but I'm sure Kumo, we'll go through it, because I'm sure there would have been people that would have tried that as well. So I'll show you what that looks like. Cool, Thelma, well done. Oh, wow. Jared, you said you don't know if they're correct, but you tried both. Well, good on you, Jared. That's cool. Well done. 100%. And even if they are wrong, it doesn't matter. We'll fix it. That's why you're here. Cool, Neo. Did you do B or E, or did you also try both? B. Cool. No problem. Okay, so we've heard from Neo and Jared and Boitshepo and Thelma. Aisha, you've also done B. Lovely, well done. Cool, Kulani, nice, good job. Which one did you do, Kulani? Or did you do both as well? Both. Oh, wow. Okay. Oh, you guys are amazing. Wow. Okay, so I'm just going to get started on, is that so enormous? I don't know. Okay, so the inverse, what you should have discovered for, maybe I should do this in green since I wrote in green over here. You should have had the inverse as 1 over 3x plus 2, right? When you drew the original function, what you should have discovered, and let me just see if I can use a, look at that. I'm so proud of myself. I've managed to work this out. Oh, there she says, and then goes and does something silly, whatever that thing is. Okay, let me see if I can move it down there. All right, so now what you would have discovered is that you would have had a y-intercept at -6, and you would have had an x-intercept at 2. All right, when you drew the inverse, let's put the inverse in purple, all right, it would have looked like this. Oh, that's not what I wanted. Hang on. And, you know, drawing these graphs are not as easy as it looks. I know I've drawn some terrible looking ones in the past. Okay, so now our x-intercept should be at -6 and our y-intercept should be at 2. And then, of course, we should have our line y equals x, which should come through the middle here. There we go. And it should look something like that. Okay, and the point of intersection you should have worked out was 3 and 3. So those of you that did B, how did that go? Was it good? Did you get the right answer? Yeah, I've been practicing, Nicole. Aisha, when you say you got -2, what did you get -2 for? Oh, you messed up the point of intersection. Yeah, Kanye, it's an easy thing to do, isn't it? Okay, for the equation. All right, so Aisha, just very quickly, I'll run through it with you, okay? So you've got y equals 3x minus 6. Interchange x and y. X equals 3y minus 6. So now if 3y stays on the right and 6 goes over to the left, can you see that it has to change its sign? I think that's what you did wrong. Okay. because you obviously then divided through by 2. Right, so now if you choose to write it as x plus 6 equals 3y, or you write it as 3y equals x plus 6, same difference. Okay, does that help, Aisha? Yeah, isn't it funny how it's those little things like that, sign changes and stuff, that's where we end up making our mistakes. You know, the actual concept we understand, but we end up losing marks on those sorts of little things. Okay, so now let me put my fancy drawing skills to better use again. All right, so we're going to leave the line y equals x there. And we're going to take away that. So I'm going to take away that and that and that. And then maybe in orange, I should leave this as y equals x. Okay, so now when it comes to us sketching the line f of x equals minus 2x, the inverse you should have written as follows. Did you guys get that? And when you sketch this line, let's go with blue, you would have ended up with a line that goes through the origin. It has a negative gradient, like so. So that would have been FO there. What you can do if you want to, especially with a graph like this where it's going through the origin, is you can determine where it goes exactly by using another point. Okay, so for example, if you want to calculate what the corresponding, let's say if I picked the point where x was equal to 2 and I worked out what the corresponding y was at that point, you guys all know how to do that. That would be the point here. It would be 2 and negative 1, for example. Sorry, that's supposed to be a bracket. All right, and then when I reflect this over the line y equals x, I can see how my x and y are going to change. All right, so now its inverse would have looked like this. Let me choose a different color. All right, I'm going to pick green this time. All right, and it would look like that. Okay, also it's got to go through the origin. Okay, so this would be the line, the inverse, and over here, one of the points that it would go through would be the opposite. So it would be minus 1 and 2, for example. Okay, but that's what it should have looked like when you reflected it over the line y equals x. How did that go? No, you're right, Johannes. It goes through the origin. The value of c is equal to 0. Okay, but no, that's quite right. Okay. Oh, good. Oh, nice. Okay, so there's some thumbs ups there. That's wonderful to see. Lovely, Matrix. Well done. Good job. Okay, so as I was saying earlier, you know, we start with the inverse of the linear function because it's the easiest one for us to draw, etc., etc. The other thing that's also really straightforward about this is that our domain and our range don't change. So, you know, if we're talking about domain and range, so it would be y as an element of the real numbers, x is an element of the real numbers. So we can't really see those changes that we would see when we're talking about quadratics or log functions or that sort of thing. So we must go and have a look at that when we do, yes, Boitshep, how did I get their coordinate 3 and 3? Oh, you mean in the previous one, Boitshep? Okay, so you've got to equate the two functions with one another. Okay, so we had, let me just go back here and look at what we had. Okay, so we had 3x minus 6, and that was equal to 1/3 x plus 2. Right, so as I was saying earlier, I like to get rid of my fractions. So I'm going to multiply everything by 3. So this gives me 9x minus 18 equals x plus 6. So taking that x over, I've got 8x. Taking the 18 over to the other side, I've got 24. And then that means when I divide both sides by 8, I would get 3. And now whether you sub into this, or the line y equals x, you're going to get the same answer for y. Okay, so y would be equal to 3. Okay. All right, Bochepo, sorted. Okay, so here the coordinates at the point of intersection, sorry, I failed to mention that. The coordinates at the point of intersection, not very exciting. It's still going to be 0 and 0. So none of that would have changed with this particular graph. Okay. All right, now that we are finished with that, are there any other questions or can we move on to quadratics? No questions. All right, cool. Okay. All right, so the inverse of many to one quadratic functions. Let's just see, there's a... Okay. Now let's consider the many to one function f of x equals x squared. Oh, sorry, Sibungile, how did you get +2 instead of -6? Hang on, let me go back. Sibungile, just explain to me what it is that you don't understand here. Do you not understand how I got the inverse? Okay, so these two functions are the inverse of one another, all right? So if my original f of x is equal to 3x minus 6, that means that y equals 3x minus 6. So now when I do the inverse, I've got to interchange x and y, okay? So that gives me x equals 3y minus 6. So now if I take this minus 6 over the equal sign so that it's there with the x, it's going to change its sign, isn't it? So it's going to be x plus 6 equals 3y. So now if I divide by 3, divide by 3, divide by 3, that's where I end up with this 1 over 3x plus 2 for y. Okay, Sibungile? All right. Okay, so let's go and have a look at this. It's a pleasure, no problem. All right, so if we consider the many to one function, f of x equals x squared, we will now draw the graph of this function as well as its reflection about the line y equals x, all right? So what we want to do when we want to draw its reflection is, of course, we've got to interchange x and y, don't we? So if this is our original function over here, y equals x squared, interchanging x and y gives us x equals y squared. Right. So now when we want to work out or make y the subject of the formula, should I rather say, we're going to have to take a square root on both sides. Now, what happens when we take the square root of a perfect square? Well, we always end up with plus minus. Okay, so we're going to end up with plus minus x. And what we would be looking at in this particular situation is that we would be considering those values of x that have to be positive. Why do we have to do that? Why can we only consider for x is greater than or equal to 0? Why would this come into play here? Does anybody know? Okay, so, okay, you're all quiet, so I'm presuming it's because you probably don't know. But remember, guys, okay, in order for a number to be real, whatever's inside your square root has to be a positive. It has to be 0 or positive. Okay, so sorry, what I was asking is that after you've interchanged the x and the y, you've now said that y is equal to plus minus root x, okay? But there's a restriction on the value of x, okay? Because we've got a square root, it means that x has to be 0 or positive. Why? Okay, and the reason for that is because we're dealing with a square root. Remember, if we've got the square root of a negative number, this would be what we would define as non-real. Okay, so that's why we've got to consider, or we can only work with those values of x that are greater than or equal to 0. Yeah, we can't square root a negative number. Okay, all right, 100%. So let's just see if there's another question. Yes. All right. So what happens now is, and I've just showed you this, we've made y squared equal to x. You've made y the subject to the formula, and now you've got plus minus root x, and then that means where x has to be greater than or equal to 0. Sorry. What? Hang on, guys. Why has it stopped sharing my screen? What happened? Sorry, I don't know where my screen went for a second. There we go. Okay, all right. Sorted, all back. All right, so the problem, of course, is that now that we have reflected our parabola over the line y equals x, we end up with this situation where our inverse is no longer a function. Okay, so I've got the original function sketched there for you. That's the graph y equals x squared. The dashed line represents the line y equals x. That's the line that we have reflected over. And here we go. All right, so over here, we've got our line y equals plus or minus root x. Okay, so that's this one over here. And can you see I've put a pink line there, right, to show you that it's failing the vertical line test. So if this fails the vertical line test, what does that mean for us?
Not a function.
It means it's not a function. Absolutely. So as it stands here like that, this is not a function. So because this is not a function, you cannot use functional notation. So you are not allowed to go f minus 1x equals plus minus root x. Okay, that is completely wrong because it's not a function, so you cannot use function notation. Can you see that's why it has been written in the form y equals? Okay, because it is not a function. So notice a couple of things. This is what I was trying to sort of point out to you earlier. All right, so we said that this was okay, provided that x was greater than or equal to 0. Look at where the graph is sketched, Matrix. Can you see that it's been sketched to the right of the y-axis where x is positive? Okay, remember x is positive in quadrant 1 and in quadrant 4. All right. Why do we say plus minus? Well, because y is positive above the x-axis. So when we are considering y equals plus root x, we are looking at this part of the parabola, this arm. Okay, let's highlight that in green. We're looking at this bit. Okay, where y is positive. If we are talking about y equals minus root x, let's highlight that in a different color. Let's go with bright yellow. We are talking about that arm over there. Okay, so that's why it's plus minus root x. Everybody happy with that? Okay, so it's not a function. It failed the vertical line test. We can't write it using functional notation. So now we've essentially got a problem, okay? But mathematicians are good problem solvers. And of course, some clever person somewhere along the line figured out a way to make this inverse relation a function, all right? Does anybody know what they did? Can you tell me rather than me telling you?
Ma'am, they placed a restriction.
Absolutely. And what did they restrict specifically, Kumo?
Ma'am, the other part of the graph.
Okay, but what do you know what that there's a special, well, not there's a special name for it, but it's called restricting the so in other words, what they did is they have yes, Kanye. Okay, they've restricted the domain, okay, the X values. All right, now I'm going to show you there are two ways in which the X values can be restricted. And depending on what they've chosen to restrict results in two different situations. Okay, so now what's important to note before we continue with this, right, is that we have to restrict the domain on the original function for its inverse to be a function. In fact, I'm going to write that there for you as well. Okay, so in order for the inverse to be a function, we have to place a restriction on the domain of the original function. Okay, so for the inverse to be a function, a restriction must be placed on the domain of the original function. Okay, so when we place a restriction on the original, on the domain of the original function, okay, what we are doing is that we are looking at one arm of the parabola that is in the quadrant where X is negative, the second quadrant, and we are looking at the other arm of the parabola that's in the quadrant where X is positive. So what we can do is we can restrict the domain based on the sign of X. So either where X is negative or where X is positive. And then we can reflect that arm over the line Y equals X, and the resulting graph will then also be a function. Okay, so the first way, let me just move that out the way. That's the first way in which this can happen. Okay, so here's our parabola. All right, what we are doing is we are looking at this arm of the parabola only, and this is where X is positive and Y is positive. Okay, so that would be like us looking over here at this bit. It's the same thing. Okay, so what we're looking at there that I'm busy highlighting in yellow right now is exactly the same as what we're looking at over here. All right, so in other words, we have restricted the domain. We are no longer considering those values of X that are negative. Now what we want to do is we want to reflect that line over the line Y equals X, right? So when it gets reflected over the line Y equals X, excuse me, it ends up looking like this. Okay, so here's the original in yellow. Okay, that's that one. That's our original. And here is our reflection in turquoise. We have reflected the yellow line over the line Y equals X. And now we've got Y equals positive root X, okay, because remember, we are working above the x-axis where output or Y is positive. And we are also considering that part of the Cartesian plane where X is positive and Y is positive. Does that make sense to everybody? Okay, I'm not reading the information that's on the left. I'm explaining the diagram. Okay. because you guys can read, and you're all welcome to go and have a look at this at a later stage if you want to. I'm not going to read that to you. Everybody happy with all of this and the restrictions that are in place and why they are in place? Sure. Okay. All right. Lovely. So now let's go and have a look at the other way in which we can restrict the domain to ensure that our resulting inverse is also going to be a function. So that's the one way that we can do it. All right. Here's the other way. Let's go over here to this guy. Okay. So now again, situation number 2, we're going to restrict the domain as follows. So now again, I'm going to do the original in yellow. All right, so this is our same bog standard parabola that we were dealing with before. So this arm that I'm busy highlighting in yellow, that is the same as this part over here that I'm now highlighting in yellow. Okay, so now we are looking again where y is positive but x is negative. Okay, so y is positive but x is negative. Okay, and that's why they've said here, x is negative, but y is going to be positive, right? So we place a restriction on the domain, all right, of our original function. So we just have that arm of the parabola that's drawn, right? We invert it over the line or reflect it over the line y equals x, and we end up with a graph that looks like that. Okay, now what we are looking at is the graph of y equals minus root x. Okay, remember we are working in that part of the Cartesian plane where y is negative. Okay, so that's why it has to be minus x in this case. But we are also only considering those values of x that are positive. And in this situation over here, as I already said, y has to be negative. Okay, so does that make sense to everyone? Are there any questions at this point? Everybody happy? Okay, so what is important to note here, Matrix, okay, it's our pleasure, all right, is that if we want the inverse of a quadratic function to be a function, we have to restrict the domain of the original function. Okay, and either it's going to look like this if we consider those values of y that are positive when x is positive, or, so that would be the turquoise one, or it's going to look like this if we consider those values of y that are negative whilst x still has to be positive. Okay, and now you can see that both of these will pass our vertical line test. Okay, so now if I do that, okay, it doesn't matter that I've got that color, can you see it's now passing my vertical line test, right? Or if I took it over to this one over here, you can see that it is now passing my vertical line test. So now it passes the vertical line test, so that means that it is a function, all right? Is it a one-to-one function or a many-to-one function? I'm talking about the inverse now.
A one-to-one.
A one-to-one. Okay, it's a one-to-one. So again, if you wanted to double check on that, you could do the horizontal line test, and you would see that it would only cut once as well. Okay, all right, and just in case anybody ever asks you that. Now, unfortunately, we have run out of time, but I will start here with you guys next time. We're going to, I'll just do one with you. We'll sketch it, we'll restrict the domain, write down the inverse, etc., and then we'll start talking about domain and range. So hopefully next time we'll have an opportunity to get started on the inverse of the exponential function. What you guys can do in terms of preparation for our next lesson, yes, because we've got the quiz to do tonight as well, don't we, Nicole, is make sure you know all the characteristics of your exponential functions from last year. I will do a revision of that with you, but if you come to the lesson prepared and learning what you need to know about the exponential function. It's just going to make life for you so much easier. Okay, anyway, so I don't know if there are any quick questions before you go off and do the quiz. No? All good? Okay, 100%. All right, Matrix, have a lovely weekend. It's the greatest pleasure. Can you? No problem. And good luck for your quiz, and we'll see you next Tuesday, okay? And good luck to those of you that are writing maths tomorrow and next week. All right.